Good, thanks.
Okay. So. Okay, so the plan that we talked about last time was to meet next time out in the field to learn about conducting a slug test. That'll be what you'll do for homework 10. So, been checking out the weather forecast, and it looks like this nice stretch of sunny, warm weather that we've had is going to be leaving. And so right now, the forecast for Monday is like in the mid 50s and rain, 90% chance of rain. Okay, so I don't want to do this in weather like that. Okay, it's just it would be unpleasant. So it may change. The forecast may change, but I'm thinking that we probably won't be going out on Monday. We're gonna have to push it back. So maybe it's Wednesday. The forecast right now for Wednesday doesn't look all that much better than Monday. So this might get pushed back to Friday, a week from today. Okay. So I guess, yeah. So if I send out an email on Sunday, everybody, is that going to be okay? Enough time for people to adjust their plans? If we're going to be, I mean, whatever you do, you're going to want to be, it's kind of a grassy field, and I mean it's pretty nice place. But if it's wet, you want to wear the right kind of shoes, and if there is a chance of rain, you'll want to wear something. So you want to know ahead of time to be ready. So if I send out an email on Sunday, is that going to be sufficient time to be ready? All right. So I'll do that. And if I say it's a go on Sunday, and then it's actually raining on Monday morning, I may cancel it and postpone it. Yeah, we've done it in the rain, and it's just, yeah, we don't want to do that. Okay, so stay tuned Sunday. I'll send out an email on Sunday saying that we're gonna go. If you don't get that email, then we'll meet here. Okay. So the default is here, not down in the field site. All right. So on the handout, there's a map to get to the field site. This is Perimeter Road. We're like right here. Perimeter Road, and then Madden Center, Old Stadium Road here. There's a traffic light right there. I think there's a new road that comes in like that now. So you can come here if you're driving. Come here. There's this is a gravel road, and there's parking down here. So come in here and park right there, and then this is a gravel road. You need to park here and walk in. The well field is right here. If you're walking, come down here, and there's an embankment here. You may be able to get down that embankment. There used to be stairs, but I don't know. I'm not sure about that. You can come in this way if you're walking too. So this is a map of there, that's a map, a location map. This is more of a geologic map. The Lake Hartwell is out here. And this is dike for Lake Hartwell. This area right here, even out kind of this region right here is below the level of the lake. So here at the well field, we're about 10 meters below the level of the lake. The Seneca River was like, it's here. It's cut off by the dike. And there's another dike up here that you see when you go along 93. And that cuts off the other end of the Seneca River. So this area right here is the floodplain of the Seneca River, the I guess former Seneca River. It's not really just a little piece of the Seneca River anymore. So this is all alluvium, like what we talked about from the coastal plain. It's a bit different than what we typically have throughout the Piedmont. Then we talked about the Piedmont conceptual model. And here, it's more like the conceptual model from the coastal plain. So there's a cross section right through there. And this is the cross section. Here's the Seneca River right there. And then this is the well field. We have wells that go down here into a sand and gravel layer. That's about 30 feet deep. It's about 10 feet thick. And that's this confined, semi-confined aquifer. And then over that is some silty clay. And the water table is very shallow. It's just a couple of feet down here. So the water table is right here. And this is all sediment that was deposited from the old Seneca River. The Seneca River was meandering back and forth over this whole area. And it was eroding and then depositing this sediment. So it eroded out here. This is saprolite, and the river eroded it out and then deposited this sand and gravel and then the finer grain material on top of it. So what we're going to do is test wells that some of them will be in this sand and gravel, and the permeability is really high. And then we have some wells up here that are shallower in this lower permeability, and we'll also test those. Okay, so that's the plan. You have this. There's my number. You know, if we're going to meet out here and you have trouble finding it, that kind of thing, give me a call. All right, so hopefully we'll work out that we can get out there soon. I want to wrap up a couple of things with constant rate tests. So what we talked about last time was analyzing the recovery part of the constant rate tests. And what we saw is we could use superposition in time. And it gave us an equation like this, where we have to, we now have this as a function of time divided by, this is the time since pumping started. This is the time since the pumping was stopped. Okay. It's that is the actual time when pumping stopped. And this is the time since pumping started. So we've basically what this is time that starts right here. Okay, this is 0 right here, and then it increases as you go on. So if we create that ratio and then plot up data using that ratio, it looks like this. This is that time ratio, and this is the early time, and then it goes and increases in slope for the late time. So we would go and fit these data with a line and get the semi-log slope and use the same equation as we would use during pumping to get an estimate of transmissivity. There it is. Okay, so we went through this. Here's the semi-log slope. I think when we did this, we saw that there was a slope of 9, and then when we did this one, it was a slope of 10. So a little bit different values for slope. All right. So there are a couple more things that we're going to want to get from the constant rate test. So this is a cross section of the well, and this is the logarithmic function of radius that we would expect from the Jacob equation. Okay, so if we measure the head out here, and then we know what the transmissivity and storativity is, and we project the head back to the well. So this is the radial distance equal to the radius of the well. Then we would get this. But in fact, what we often find is that the head in the well is greater than, or less, the head of the well is less than that, lower. And the drawdown, right, which is this distance, the actual drawdown is greater than the drawdown that we would predict using the Jacob analysis. Okay, so the reason for that is that when wells are created, or sometimes when they're used, there can be processes that cause the formation next to the well to get plugged up. So the permeability here is less than it is out here. So if we just took that little slice, the transmissivity would be less than that transmissivity. And as a result of that, the losses of the hydraulic head are greater through this zone than they would be through this zone if the transmissivity was what we thought it was. Okay, so this is called a well skin, or a damage zone around the well, and it causes increased head loss. So remember we said the hydraulic head was the energy in the unit of volume. We lose more of it here as a result of this skin. That reduces the efficiency of the well. You know, we've got a pump here, and we're only going to be able to draw the well down to a certain level before we start interfering with the pump. So if we have a drawdown to here instead of here, it means that we're going to be getting closer to the pump, and we're going to be more close to the limit of what we can pump out of the well than what we thought. So it's important to be able to keep or factor in this effect. So the way that we characterize this is with the well efficiency. And the well efficiency is going to be the ratio of that drawdown to that drawdown. So it's this drawdown divided by that. So when the drawdown that we're actually seeing is greater, then we have a well efficiency that's less than 1. Okay, that means that there's some kind of a skin around the well. So the way we're going to calculate that is to go and do the analysis that we saw last time, where we go and we fit the semi-log slope and we get T from the semi-log slope, and then from the intersect we get S. And then we're going to take the results of the test. Typically it's towards the end of the test, and we're going to use this equation to predict what we think the drawdown should be at the well. So the important thing is that we put in the radius of the well here, and this time there'll be some time when we measure the drawdown, and we want to use that same time here. So we put in that time, put in the radius of the well, and we predict what the drawdown is. This is the drawdown that's expected if the entire formation has these properties. So we do that calculation, take the ratio with what the actual drawdown is that was measured, and that gives us the well efficiency. Okay, that allows us to relate the drawdown that we would calculate from what actually happened. Okay, so another effect that we want to evaluate is the well performance and the longer term well performance. The kind of results that we've been looking at here, we can get from pumping the well for, I don't know, an hour, a few hours, short term, maybe a couple days. But if we use the well for long term, then our assumption that we use for the analysis is not going to hold, because our assumption was that, well, it might not hold. Our assumption was that the aquifer is infinitely large in lateral extent. Okay, so start pumping, the drawdown goes out, and so long as the aquifer is uniform and we don't encounter any changes, then the well thinks that it's in an aquifer of infinite extent. No aquifers actually are, but if the actual extent is much bigger than the radius of influence, then the well thinks that it's in an aquifer of infinite extent. We can use the analysis. But the longer we pump, the bigger the radius of influence is, the more likely that we're going to interact with some boundaries. And that's going to change the well performance compared to what we were analyzing when we assume that it's infinite. So we have a well here and a monitoring well. Then this is what we've seen. This is the log of time. This is what we've seen. If there's a no flow boundary, so maybe the aquifer just ends here. And if that's the case, if we were assuming that it was infinite extent, it would do this. If in fact there's a boundary and the aquifer is not here, then we need more drawdown to get the same amount of water out that we would have if the aquifer was here. So the curve starts to steepen when there's a no flow boundary. And then similarly, if this is a stream and this is a shallow aquifer, then when the drawdown goes to here and reaches the stream, we can get water out of the stream instead of getting water out of storage. And that means that the drawdown could be less than it would be for that case. Okay, so those are some things that can affect the drawdown. In all three of these cases, up to this time, the well thinks that it's in an infinite aquifer. It doesn't know about the boundaries yet. So we can use this to estimate the aquifer properties. But then after this happens, the slope is no longer going to give us the transmissivity. Okay. So we can analyze this case too. And we can go and do the analysis where here's the well, here's a boundary. And we can use the same process of superposition that we use to do recovery. What we did before was to use superposition in time, but here we can do superposition in space. So this is a cross section of a well with the drawdown, and it's infinite extent, so it's just continuing on. So the way that we include a no flow boundary right here is we use what's called an image well. And this is an imaginary well that we put in here. and it's set away from the boundary, the same distance that our well is from the boundary. So if the well is a distance L from the boundary, then this image well is also a distance L from the boundary. It's a distance equal to 2L from this well. Okay, so put in that image well, and we say that if we're pumping out of this well, then we're pumping in to this well. Okay, so that means that if the water level starts here, then at some time the water level from this well has dropped to here. But here, if we're injecting, the water level rises and it looks like that. And I just took these lines and flipped them over and dragged them over here because these curves are the same. They're just mirrored and slid over here. But the important thing to see is that right here, the drawdown is equal to the buildup here. These are equal. So if we add them together, it's 0. So we add these two functions together. There's the image well. And yeah, so if we add them together, the drawdown will be equal 0. If we do this, and we say this is a pumping well, that's a pumping well, we add these two together, then we get more drawdown here. But the thing that we see here is that there would be the drawdown would look like that, so there would be a no flow boundary right here. The slope would be 0. So we can do this kind of superposition to make a no flow boundary. We do the other kind of superposition where this has an injection well to make a constant head boundary. Okay, so here's the way we can set this up as an analysis. So we say that the total drawdown is equal to the drawdown from the well and the drawdown from the image well. So here's the well, just the Jacob analysis. And then here is this should be the well. This is the well where we go from r squared to x squared plus y squared. Okay, so we've got to use an xy coordinate here. And so that's just the change that we do there. There's image well. And this image well, what we're going to do for the drawdown at this image well, we're going to change the sign. And then instead of x squared, we make it x minus 2L squared. Okay, so that's 2L. So x minus 2L is just like taking this well here and sliding it over to here. Okay, so this is the equation for the drawdown around the image well, and essentially identical with the change in sign and this slight change in the coordinate system. But that's the key difference. So we put these two together, and there's the x squared, y squared, there's the x minus 2L squared, and there's the negative sign. So when we bring these together, we have the log function, and so if we take this log minus that log, we can then take it's basically then going to be the log of this times 1 over that. That's what you get when you factor out this thing, and then it's log of that minus log of that, and it just becomes basically going to be this divided by that. There's the x squared, y squared in the denominator, and there's this thing here in the numerator. Okay, so that's what you get for the drawdown. Here's that result. If we take it, we say y is equal to 0. What we want to do is get the drawdown at the well. So y is equal to 0, and x equals the radius of the well. So let me show you how to. So we say y is equal to 0 at the well, and x equals RW. Okay, so right here, we have RW minus 2L squared. Okay, what we're trying to do is get this simplified so we can have it be a more convenient for calculation. So this is the radius of the well right here. And 2L is this. Right, there's 2L. So RW is way smaller than 2L. So if we take the difference of this, we can just say that this is going to be approximately equal to 2L squared. Okay, so this thing then becomes 2L squared, and this is RW squared. Okay, so this thing here just goes to that. And then if you take the log of this stuff with the 2 comes down and you have that. Okay, so this is the total drawdown here at this well as a result of this boundary. Once everything's gone to steady state. So what we can do then is to go back and recall this quantity of the specific capacity. This is the pumping rate that we can make from a well as a function of the drawdown. So the ratio of the pumping rate to the drawdown. So we just bring this over here and invert it, and then that gives us the steady state specific capacity. So if we want to evaluate the performance of the well in terms of how much water it might be able to produce at steady state, then we can do this calculation, and this gives us an estimate of the drawdown based on this ratio. So in order to get what the actual flow rate is, we need to say what kind of drawdown are we able to tolerate. So this is going to be based on how deep the pump is. We have to keep the water level above the pump, usually several feet at least above the pump. So we'll be able to specify what the drawdown is, the maximum drawdown we can tolerate, and that'll allow us then to estimate Q. Okay, so we go through, do the analysis, we come up with T, like we talked about, and then what we need is the radius of the well and this term L, and this is just the distance to the stream. Okay, so this gives us another simple way to evaluate a pumping test and estimate the well performance. So we had this as an example, and we've done the analysis for T and S and the recovery. I went in and did this out by hand. So here's T and S, and then the well efficiency. This is the well efficiency calculation. Okay, so this is the Jacob analysis, and I have the drawdown after 1,000 minutes. I think this is in the handout. We're given the drawdown after 1,000 minutes. The radius of the well is 0.25 feet. This would be the handout from yesterday or from last time. Okay, so I guess it looks like what's given in the handout is that the drawdown after 1,000 minutes of pumping is 90 feet. That sound right from last time?
I don't remember getting this handout.
Yeah, I mean, it's this handout. So this handout, the drawdown of a well is 90 feet after 1,000 minutes. Okay, from last time. So there's 1,000 minutes for the time. This is the radius of the well. And we go through, do the calculation. I calculated this part here, writing the units out, and got 9.15 feet. And then, the log here, this is going to be dimensionless. This part here the units have to all cancel out. That's one of the rules for the argument of a log. So we can check and make sure that that's the case. So I wrote this all out with the units. The units here just to check. And then I got 9.15 feet from this coefficient up front and log of 5, and it ends up being that. So 61 feet of drawdown is what we would expect if the transmissivity is equal to that everywhere. In fact, we see that the drawdown is this, so we take the ratio, and that's the well efficiency. Okay, so that's how you go about doing that. And then this is the steady state specific capacity. And we're given L as, I guess, 150 feet. Go through and do this calculation, and it's 0.12. And what you can see here is it has the same units of as transmissivity, right? It's 2 pi t times 1 over log. That thing there is dimensionless. The log is always going to be dimensionless. So it has the same units as t. Well, it's the flow rate, which is volume per time divided by the drawdown. So you can think of it in terms of unit of P, or you can think of it in terms of a volumetric rate per unit of drawdown. So go through and do the calculation. And here I'm writing it out as the specific capacity is 0.12 cubic feet per minute as a rate per foot of drawdown. Okay, the units that you get are feet squared per minute, but this is, I think, easier to understand. Okay, any questions on that? This is in the PowerPoint on Canvas. It's a couple of slides down from where I have showed it. I moved it up, but you can go and check it out there if you want. Okay, so okay, so what we're going to do when we're in the field is conduct a different kind of test. This is called a flow test. And we look at constant rate tests, and the slug test is going to be the response of the aquifer to a different kind of stress. In this case, we're going to change the drawdown suddenly, and we're gonna see how the aquifer responds to it. So what's being done here is to take this weighted cylinder and drop it into the well here, and it'll displace the water. The water level will rise, and well, we'll drop it in the well. I think here's a graphic. So we take this cylinder, drop it in the well, that raises the water level. And at this point, okay. So we start out here, and this is the initial water level here. So system is in equilibrium, and drop the slug in. That displaces the water up here. Okay, so at this point, we've got a big difference in the hydraulic head. Here's a confining unit, so the screen is here. So the head right here in the aquifer at that point is there, but in the well it's here. So there's a big gradient in hydraulic head between the well and the aquifer. So that causes water to flow out into the aquifer, and that causes the water level to drop. And up here, this is the hydraulic head. So the head of the well is dropping, and keep going. It keeps dropping, and up like so, and then pull it back out, and the water level drops as a result of the slug coming out, and then the water level will rise back up. Or when the slug comes out, the water level drops and is now below the static water level in the aquifer, and it comes back up. Got it. Okay, so what we want to be able to do is analyze this, and there are a couple of different ways of doing this. What you find is that this decay is like a negative exponential. So this is like a constant times e to the minus at. Okay, so it's starting out at this time or at this level when we start keeping track of the time, the water level drops with time and decays back to the original. Okay, so the response to this sludge test is just like an exponential decay type of process. So if we write this as a semi-log, if we write it like this, then this will be a plus the complement. And this ends up, and then if we plot it as a semi-log where it's a log scale on y, then this becomes a linear function. Okay, and the relationship is that the log of h over h0, this is the head during the test. This is the initial head. So this starts out as 1. And this equals minus, that's the hydraulic conductivity. That's the radius of the well. And that's time. Okay, so if we were to take the exponential of both sides, we would get h over h0 equals e to this stuff here. The G is going to be a geometric factor that allows us to do this analysis for various different geometries. Okay, so the way this is going to work is that if we substitute in h over h0 equals 0.37, then the log of 0.37 equals -1. Okay, so if I make this, let's see. So if I make this 0.37 a particular time, then that becomes -1. And the way to think about that is that this is 1. Okay, this is h over h0. So h0 is the starting head. And if we take this, the initial head at time of 0 is equal to h0. So it starts at 1 and then decays down, and 0.37 is right there. So it's decayed by 37%. Go out there to there, that is t 0.37. Okay, so at that particular time, this becomes -1, and we can then solve for k. Okay, so the minuses cancel, and k is going to equal pi r w squared g. Okay, so we do a slug test, we measure the head as a function of time. We get this particular time when his head is decayed by 0.37. That goes there. This is the radius of the well, and this is the geometric factor. Depends on the geometry. I'll show you some examples. But here's one case that was developed by this guy Borslev, and he was really one of the pioneers of slug test analysis. This is his work was back in the 50s and 60s. He came up with this geometric factor along with a variety of others, and he gets a named equation. The Borslev analysis of slug test is the simplest, and it's probably the most common analysis of slug test. So in addition to Borslev, Borslev is that particular analysis. Let me go back a second. That particular analysis is for this case. This is the geometric factor for a fully penetrating well in a confined aquifer. So we have something like this. Here's the confining unit, and the well is the well screen goes completely through the aquifer. Okay, so the screen could be short, and it could be up at the top or at the bottom. So there are a variety of variations on where the screen can be within the aquifer, and those change the geometry. Having a well where the screen fully penetrates is the simplest geometry, and that's what Borslev did. There are more complicated geometries And a more general case looks like this, where the screen here, the screen is here, and that's LE. And then the screen is down below the water table, and above the bottom of the aquifer. So to describe this geometry, you need to know the well screen and how deep it is and how far above it is. So the three lengths are this length here of the screen from the water table down to the bottom of the screen, and then B is the entire saturated thickness of the aquifer. So if we wanted to analyze a geometry like this, we can do it with the analysis from Bauer and Rice. That's a more realistic geometry, and we can then calculate a geometric factor that allows us to simulate or account for this geometry. We have another geometric factor that we came up with using a program that we developed called DFRAX, and it gives a geometric factor between 0.8 and 1.4 for fractured rock. And you can approximate it as 1.1.0, so it makes it simpler. So here's the way that it's going to work. The transmissivity for what I would call basic slug test analysis, Horslev, the Bauer and Rice, and the DFRAC, those are all what I would call basic slug test analysis. And they're going to be, the transmissivity is going to be, this is the diameter of the casing squared. There's that T.37, and then this is the geometric factor. Okay, so this is the Horslev analysis, and here's the geometric factor for that case. All right. One other point here is that for the slug test analysis, we need to consider a well that so here's a simple sketch, but when we saw wells being constructed, we saw that there was many wells are going to be built like this. So this is a seal, and there's a sand pack here, and then this is the casing. Okay, so this is the diameter of the casing here, and if we have a water level that starts here and goes up to here, the volume that is involved in the slug test is determined by the diameter of the casing. But this is the diameter of the gravel pack. So the well, when we're interacting with aquifer, another diameter that's important is going to be the diameter of the gravel pack. So in the analysis, that's called D, capital D, and this is called lowercase d. Okay, so here's the basic analysis, and on the handout, I gave you an example that we want to go through. This is going to be the Horslev analysis. We can go through and give it a try. What you get when you take this equation and plot it on semi-log paper, where this is now a log scale, it makes that curve straight, makes that exponential function in a straight line with a negative slope. So what you do is plot the data on here. These are measurements from the field, and fit this with a straight line. And then here, 0.1, 0.2, 0.3, 0.37 would be like right in here. Hit the fit line and then go down to get the T.37. So why don't you go and try this out on your own and we'll take a look at this when we get back to class. Probably Monday, but maybe Wednesday. Have a good weekend.
Good evening.